Section 1.2. In this section, we're going to see a lot of vocabulary, and we're also going to see a lot of things that you've studied already in pre-calculus, like Gauss-Jordan elimination. So the first word that we're going to define today is a matrix, and this has just to be viewed as a rectangular array of numbers, so it's just numbers or entries that are numbers in a rectangle. And we say that it's an n by m matrix if it has n rows and m columns, and that is called the order of the matrix. Now if you are looking at a 3 by 5 matrix, it means it has 3 rows and 5 columns, and 3 rows, to count them you have to count them in a column, right? So you count 1, 2, 3 down a column, and that gives you the number of rows, and then 5 along a row gives you the number of columns. So it's a little bit counterintuitive sometimes. If m is equal to n, then it's an n by n matrix, and this is called a square matrix. Now the entries of the matrix are all the numbers, and to find one of them, to identify one of them in a matrix capital A, we can call them A sub ij, and that means it's the number that is in the ith row and jth column. So for example here we have a 3 by 5 matrix. Always just get into the habit of counting down and across. So 3 by 5, 3 rows and 5 columns, and the entry A23 is this entry right here, second row, third column, so it's a 1, and the entry A15 is this one right there, it's 12. For a square matrix, the entries A11, A22, ANN correspond to the main diagonal of the matrix. We can just say the diagonal because we pretty much never look at the other diagonal, A1, A2, n-1, the diagonal going this way. It never, well, not never, but it's very rare that we are interested in that diagonal. If all the values in a matrix are 0 except the entries in the main diagonal, then we call it a diagonal matrix. And if all the entries that are below the diagonal are 0, we say that the matrix is an upper triangular matrix. This is an example. So the diagonal is the numbers 1, 4, 6. Above the diagonal are all the numbers that are above the 1, above the 4, above the 6, and then the numbers below the diagonal are 0, 0, 0. So this is an upper triangular matrix. And how would we express that? We would say that A sub ij is 0 if I is greater than j. So if the row number is larger than the column number, then the entry has to be 0. For example, this is A31. We see that I, which is 3, is greater than j, which is 1, and so it's a 0. Similarly, we have lower triangular matrices, and it's just the opposite. This time it's the entries above the diagonals, the main diagonal, that have to be 0. Finally, the matrix that has all zeros is just called the zero matrix. So here we have 3 matrices, and we want to use a few of the words that we've just seen to define them or describe them. So firstly, we can say that it's a 3 by 3 matrix, we can say that it's a square matrix, we can say that it's an upper triangular matrix. Matrix B is also a square matrix, it's a 2 by 2 matrix, it's a diagonal matrix. Matrix C has order 2 by 3. It is not an upper triangular matrix because it is not a square matrix. You have to qualify by being a square matrix before you can even be considered as a diagonal matrix, an upper triangular matrix, or a lower triangular matrix. Now, among all the n by m matrices, some of them are special and they have even their own name. If a matrix is n by 1, then it is a column vector, n by 1, and if a matrix is 1 by m, then it's a row vector. So we will write vectors this way in linear algebra. Now this is a choice of the textbook. It's a different choice from what we did in multivariable, but you should be ready to see either in the further textbooks that you will read in your career. So again, in linear algebra, we will write vectors typically in columns 1, 3 with square brackets. So if we consider all vectors that are possible, then we denote that to be Rn. In multivariable, we may have considered that the objects that belonged to Rn were points. The point, for example, in R3, the point 157 is an element of Rn, and 238 is another element of Rn. In linear algebra, we will kind of make a switch and consider that the elements of Rn are the vectors. So vector 178 is a vector that is an element of R3. A vector can be represented by an arrow from the origin to the point that corresponds to the components of the vector. And we will do that a lot when we try to have geometrical explanations to the concepts that we study. Here are more definitions. This is a system of equations, and with a system of equations you can write the coefficient matrix that corresponds to it. And furthermore, you have the augmented matrix, which includes the constant on the right side of the equality. So when we have pen and paper, we typically put dots along a column here, just to show this is red x minus 4y plus 3z equals 5. If you ever use your TIA-Nspire though, you're not going to put these dots, you're just going to type it as a 3 by 4 matrix like this. Elementary row operations. We are going to see these again, and I'm going to rely on what you've learned in pre-calculus here. The elementary row operations, there's 3 of them, are the things that you're allowed to do with matrices when you're trying to solve a system of equation using matrices. One of them is that you're allowed to switch rows, and it's really essential that you always keep in mind what you are actually doing to the equations themselves when you do these elementary row operations. When you switch 2 rows, it's like switching 2 equations, and it's pretty obvious that this is not changing the solution to the system of equations. When you switch the equations, you put the first one in the second position or in the third position. Another thing you're allowed to do is to multiply a row by a non-zero number. For example, if you have the equation x plus y equals 7, then you can write 2x plus 2y equals 14. Of course, since you're allowed to multiply, you are also allowed to divide by any non-zero number. And then the last thing you can do is to add a multiple of a certain row to another row. And this is what we do when we solve using addition. This is pretty much what we do. We set up 2 equations to have maybe 3x, and the other one has negative 3x, and then we add them together and it cancels out the x. This is the effect of the third row operation. You can add to a row a multiple of another row. Of course, you can also subtract to a row a multiple of another row. So we are going to use these elementary row operations to reach the reduced row echelon form. And there's 2 terms here that we will define later on, but as we go through them, we will introduce them for the first time. The goal is to have 1s along the diagonal and 0 everywhere else. And the effect is going to show up in the last column of the augmented matrix. So firstly, make sure that you know how to write an augmented matrix. This is 1x minus 4y plus 3z equals 5. So the augmented matrix is 1, negative 4, 3, 5. 1x minus 4y plus 3z equals 5. You do the same with the other two rows. Now, if you are writing what you are doing in each step, then this is the way I like to write it. This means row 2, to row 2 I add row 1. So if we look at what happened, negative 1 plus 1 equals 0, indeed. 3 plus negative 4 equals negative 1, indeed. And negative 1 plus 3 equals 2. Finally, negative 3 plus 5 equals 2 as well. Sometimes we can do two rows or two operations in one step because they don't interfere with each other. And this is what we did in that example. To row 3, we added 2 times row 2. So we added 2 times this row 2. It refers to the previous augmented matrix. So why are we starting with these two steps? We can see that we got zeros here and there, and again the goal is to have zeros everywhere under the diagonal, ones across the diagonal, and zeros above the diagonal. You can do that in many different orders, but some orders are going to be more efficient than others, and for me this is the order I favor. So first I try to get a 1 in the first entry of the matrix, and then I try to get zeros below that 1, and then I try to get a 1 in the second entry on the diagonal, and I try to get zeros below that, etc. So for a 3 by 3 matrix, there's these first 6 steps. So as you can see, we were given a 1 in the first entry of the diagonal, which is awesome. First step is done, and then here we managed in one step to fix the next two steps of the process. Next step is to get a 1 here, so from negative 1 I'm going to multiply this row by negative 1, which yields 0, 1, negative 2, negative 2. And once I've done that, I can also focus immediately on the 5th step, which is to get a 0 here. So if I compare these two rows, what I'm going to need to do is row 3 plus 6 times row 2. So this is written here, row 3 plus 6 times row 2. So we have reached almost the end. All we need now is to get a 1 here, and that's very easy. We're just going to multiply the third row by 1 over 6, and we are done. This stage here is called row echelon form. It's written REF often. From here on, we can continue and set up the last 3 entries that we are interested in, and here this is the order I go in. I try to get a 0 here and then zeros in these two positions. So for my first goal to get a 0 here, I'm gonna be working with row 2 because that's just a way to do it. What's good is since there's a 0 in column 1 now, I'm never gonna affect this value, so that's great. So row 1 plus 4 times row 2 gives me what I need, and then I can conclude with the last 2 steps. So in the end, I get, if I read what this means 0x plus 0y plus 1z equals 2, so z equals 2. Here, if I read this, it means y equals 2, and here x equals 7. I could have solved the system of equations stopping at the row echelon form because we already had z equals 2, and if I know that z equals 2, I can work backward and find that y minus 4 equals negative 2, so that gives me y equals 2, and if I know y, I can do x minus 8 plus 6 equals 5, so I can find x equals 7. So formally, row echelon form is something like this, where firstly all the rows with only zeros are placed at the bottom here. Then the first entry in each row that is not a 0 has to be a 1. So you can see here the first entry that's not a 0 is a 1. Here again the first entry that's not a 0 is a 1. And here again. This is called the leading one. In other textbooks, this is called the pivot. In our textbook, it is called the leading one. Lastly, last requirement, a leading one in any row has to be further to the right than the leading one in all the rows above it. So it creates echelons. Echelons is the same root as escalator. It creates steps like this. So the ones have to always be further to the right than in previous rows. Secondly, a matrix is in reduced row echelon form if it has one additional property. So all the properties from earlier still apply, but moreover, every entry in a column above a leading one has to be a 0. So notice above this leading one there is a 0. Above this leading one there are zeros. Sometimes you have columns that don't have a leading one, so this rule doesn't apply to them. The echelons here you can see go like that. So there's no leading one here, so there's a 5, there's nothing we can do about it. It still qualifies as being in reduced row echelon form, or RREF. Same with the last column. So let's look at these examples here. Which ones are in reduced row echelon form, or reduced echelon form, or nothing. The first example is none, just because there's a row with 0, this row should be at the bottom. If we switched row 2 and row 3, we would get what we need. It would be in RREF. The second example is in row echelon form, not reduced row echelon form. The problem is there's a 5 here, so if there was a 0 here, it would be RREF. Finally, this matrix here is in reduced row echelon form. So if you're trying to get to reduced row echelon form and you're working with a friend and you compare your solutions when you reach row echelon form here, you may not have the same answer. That does not mean that you made a mistake, because there are many ways to reach row echelon form and they may not all be exactly the same. However, if you keep on going until both of you reach reduced row echelon form, then that matrix is unique. Okay, some questions that are going to refer back to thinking about system of equations. If someone solves a linear system of equations and reaches the following matrix, what can we say? What we see is that the last row spells 0x plus 0y plus 0z equals 2. So basically 0 equals 2. That automatically means that the system of equation has no solution. In another situation, we reach the following reduced row echelon form, and we can see that the last row says 0x plus y minus 3z equals -1. What that is going to mean is that there are infinitely many solutions. I can choose z, whatever I want it to be, for example 5, and then it'll yield me a value for y, but I can choose z to be another value. So there's infinitely many solutions. So there's going to always be 0 solution, 1 solution, or infinitely many solutions, just like we saw in section 1.1. This is not just true of numbers, it's always going to be true in when we solve matrices like that. Okay, so if we want to solve this system of equations using what we've learned, we are going to write the augmented matrix, and then step by step we are going to reach a row echelon form. And what we notice here is that the last row is 0, 0, 0, 0, so nothing comes out of here, but in the second row we get y plus 5 over 4z equals -3 over 4. If we want to write the solutions to this system, we want to go further than just saying there's infinitely many solutions. Even though there are infinitely many solutions, there's something we can say about these solutions. If you think back at the previous section, we had noticed that when we have 3 planes, the solutions are on a line typically. So we can describe what this line is. And to do that, we're just going to say that z is a parameter t. So we just define z to be t, and t is a value that we can choose later on. And that, in turn, means that y is equal to negative 5 over 4t minus 3 over 4. And this, if we proceed one row further up, x is equal to negative 2y minus 3z, which is equal to, if we substitute our values for y and z that have t, is equal to negative 1 over 2t plus 3 over 2. So the solutions are on the line that we could write in parametric equations. For example, x equals negative 1 half t plus 3 over 2, y equals negative 5 over 4t minus 3 over 4, and z equals t plus 0. Any specific value that you would want to find, you can just choose t, and it'll yield a solution to this system of equation. So that wraps it up for section 1.2. Lots of vocabulary and a first step into manipulation of matrices. Thank you very much for listening.